Hello everyone, my name is Mingyu Lee. I'm an undergraduate researcher at Georgia Tech. Today I will present recap a training pre-compensation method for coarse activation channel pruning in compressed large language models. LLMs face a fundamental scaling challenge. As LLMs continue to grow in size, computational and memory costs increase proportionally. As shown in the figures, models like Llama 2 to Llama 4 have dramatically increased in size over time. While this scaling improves performance, it creates significant barriers for deployment, particularly in resource-constrained edge environments. Post-training compression techniques have emerged as critical solutions for efficient LLM inference. These include diverse methods such as pruning, removing ineffectual parameters, quantization, reducing bit precision, and techniques like SVD, distillation, and token fusion. In this work, we focus specifically on pruning methods. LLM sparsity can be categorized into three types: weight sparsity, input sparsity, and output sparsity. Weight sparsity removes ineffectual elements from weight tensors. Input sparsity removes ineffectual activation elements. Output sparsity applies binary mask after activation weight multiplication to prune corresponding elements. In this work, input sparsity is selected. In pruning, there are diverse patterns based on granularity, and they present different trade-offs between hardware efficiency and model accuracy. Unstructured sparsity offers minimal accuracy degradation but limited hardware acceleration. NM sparsity provides balanced hardware-software efficiency with moderate accuracy degradation. Channel sparsity offers low computational complexity and hardware-friendly implementation, but typically results in significant accuracy loss. For unstructured sparsity, works have focused on designing sparse gem accelerators such as Sigma, a CNN EIT code. And for NM sparsity, works have aimed to optimize with fine-tuning and searching adequate ratios for each layers, such as PAS-D or A100 GPU support. Our work recap specifically targets channel sparsity, aiming to recover its accuracy loss through training-free compensation. Recap consists of three key steps. First, channel pruning, applying magnitude-based channel pruning to remove channels with lowest absolute averages. And second, statistical analysis, which we reuse the pruning-induced statistics to characterize recoverable errors. And lastly, in compensation stage, we perform lightweight operations such as element-wise weight scaling and sign-guided accumulation to generate compensation factor. This approach achieves substantial improvements, plus 34% accuracy increase in OQ benchmark for Llama 3 8 billion model at 70% sparsity, and plus 23% accuracy increase in 5-shot MMLU for QN 2.53 billion model at 30% sparsity, also with massive perplexity reductions across all evaluated models. To dive deeper into recap procedure, we consider a typical gem operation, matrix multiplication between activation A and weight W, producing output O. Conventional channel pruning selects top K channels using the absolute average magnitude M with indices I. Pruned activation A prime and corresponding pruned weights W prime yield a reduced gem for output O prime. Channels pruning introduces two types of errors, recoverable and irrecoverable. Recap targets the recoverable error component through efficient compensation. We compensate recoverable errors by first reusing the pruning statistics on element-wise weight scaling to produce W scale. Then, sign-guided accumulation is applied to W scale using sign bits from activation elements, which is essentially lightweight addition and subtraction operations, generating a compensation factor epsilon. Finally, the compensation factor epsilon is added to O prime. For better approximation of epsilon, we implement group channel sparsity. We compute magnitudes at finer granularity with group size ng and perform grouped weight scaling and accumulation. Then we concatenate generated errors for final compensation factor epsilon. This strategy captures localized activation distributions and handles outliers effectively within the channel. We evaluate recap on a llama family, llama 2.7 billion and llama 3.8 billion model, and QN 2.53 billion models. Evaluation metrics include perplexity on Kitex2, zero-shot Q, 5-shot MLU, LSWAG, and qualitative text generation analysis. Target layers includes query key value and output projections, plus feed-forward network layers. Implementation used PyTorch with NVIDIA GH200 GPU for inference and empirically determined group size ng as 8. First, we show the results of perplexity. As shown in the table, naive channel pruning dramatically increases perplexity across all sparsity levels. However, recap achieves massive perplexity reductions across all models and sparsity ratios, approaching baseline model performances. On BOQ and MMLU benchmarks, naive channel pruning causes substantial accuracy degradation. However, recap significantly recovers this lost accuracy. For example, on llama 3 8 billion model at 70% sparsity, naive channel pruning loses 43% BOQ accuracy, while recap recovers 34% accuracy. On QN 2.53 billion model at 30% sparsity, channel pruning loses 39% of 5-shot MMLU accuracy, while recap recovers 23% accuracy. Text generation experiments demonstrate recap's effectiveness in mitigating semantic distortions. While naive channel pruning produces incorrect responses, such as elephant or largest animal, recap generates correct answer as blue whale, indicating preserved semantic understanding. Also, for input about LLMs, channel sparsity falsely describes as a language, while recap properly refer it as an artificial intelligence model. A Bayesian study on group size shows that larger ng values improve perplexity by better capturing skewed channel distributions and handling outliers within the channel. We select ng as 8 to balance accuracy and efficiency. We also compare recap with TEAL, which they apply greedy optimization for non-uniform layer-wise pruning approaches. We employ flow at targeted sparsity of 60% for non-uniform layer-wise pruning. Experiments demonstrates that recap achieves approximately 5% higher benchmark accuracy than TEAL, highlighting the effectiveness of recap's compensation for pruning-induced errors. The table shows BOQ and LLSWAG benchmarks. For future research directions, we are planning to do a theoretical foundation and combining with weight compression. Specifically, we plan to theoretically validate our method and also develop a formulation for the unrecoverable error component delta. Also, since our technique is orthogonal to existing weight compression methods, we plan to integrate recap with diverse quantization techniques for weights. Recap presents a lightweight training-free channel pruning compensation method that reuses pruning statistics for error recovery. Key innovations include training-free compensation achieving up to plus 34% accuracy, recovery, and substantial perplexity improvements. Recap highlights the potential to bridge the gap between hardware efficiency and software accuracy in the context of pruning, offering a promising future direction of exploration in efficient LLM deployment. Thank you for listening.